Okay, so in the last video we saw this proposition which says that if G is a graph, then it has a path of length at least delta G, in fact a path of length delta G, where delta G is the minimum degree of G, and a cycle of length at least delta G plus 1, provided the minimum degree is at least 2. Note that although this proposition tells us something about the existence of a cycle of, say, at least this length in the graph, but it does not say anything about the girth of the graph, which is the length of the smallest possible cycle in a graph. So these two things, minimum degree and girth, in general are not related. Are not related. That is, one does not determine the other or bound the other in any way unless we fix the number of vertices in the graph or the order of the graph. As we shall see in chapter 11, there are graphs of arbitrarily large minimum degree and arbitrarily large girth. Okay, next we define the distance between 2 points in a, two vertices in a graph. The distance between two vertices, say U and V, in a graph G is defined to be the length of a shortest UV path in G. Or we have to say the other, the other possibility also has to be defined. If no such path exists, we define the distance to be infinity. That is, we treat the vertices as being infinitely far away from each other. we denote the distance between u and v by this. The subscript g tells us that the distance is being calculated in the graph g, or simply by du comma v. Let's take one example which will help us understand what this thing is about and what this g, why this g is needed. Say we draw a graph and let's name the vertices also. 1 2 3 4 5 6 7 say, and suppose this graph is g. And one more thing, let us also join the vertices 1 and 3. Suppose this is g, whereas let's draw another graph h, which is just like g with only one difference. In h, 1 and 3 are not adjacent. In other words, h is actually a subgraph of g. Oh, sorry. 1 2 3 4 5 6 and 7. Suppose this is h. Okay, now say we want to calculate the distance between 1 and 3 in G. We look for paths between 1 and 3, that is a path joining 1 and 3. There are a number of such paths. One of them is this. It goes from 1 to 4 and then from 4 to 3. Okay, so that is one path. Another path is this 1 2 3, but we have another path which is this. The lengths of these two paths, that is 1 4 3 and 1 2 3, are equal to 2. Both of them are of length 2. However, this path 1 3 is of length 1. And you can clearly see that this is the shortest possible path between 1 and 3, and that is why the distance between 1 and 3 in G is 1. However, if we look in H, then here that path is missing. So here we have to only consider these two paths 1 2 3 and 1 4 3. So in h, the distance between 1 and 3 will be 2, because that is the shortest possible length of any path joining 1 and 3. So it does matter in which graph we are calculating the distance. So that's why we use the subscript. But if we have only one graph with which we are working and we are not changing the graph, then we can drop the subscript sometimes if there is no chance of confusion. So that is the concept of distance between 2 points in a graph. One more thing is this. Say you have a graph that looks like this. You can draw any other type of graph not having any cycle or a force cycle like this. And that is, by that I mean a square. But I just want to illustrate the notions, that's all. So if you have a graph like this, say 1, 2, 3, 4, 5, 6, 7. So this graph is I. Then the distance between say 3 and 6 in I is infinity. There is no path joining 3 and 6 in I. And in fact, here itself, if you consider that subgraph which is obtained from G by deleting the edge 3, 5, you have everything else of G in that subgraph except the edge 3, 5. Then in that subgraph, the distance between say 3 and 5 will be infinity. However, in G, the distance between 3 and 5 is 1. So these are all the things that have been said in the definition. The greatest distance between any 2 points in a graph G is called the diameter of G and is denoted like this. Okay. For example, in this graph say, or for example in this graph, in this G itself, what can the diameter be? You have to look for the distances between any 2 points. For example, the distance between 1 and 3. Just let us, for this graph, write all the possible distances. Distance between, we go systematically, 1 and 2. Since we are in G, so we choose to not write the subscript. The distance between 1 and 2 is 1, or okay, you may confuse this with the other graph. So let's just write the subscript. The distance between 1 and 2 is 1, which is also equal to the distance between 1 and 3 and the distance between 1 and 4. the distance between 1 and 5 is 2, and the distances between 1 and 6 and 1 and 7 are equal to 3. Then the distance between 2 and 3 is 1, that between 2 and 4 is 2. Between 2 and 5 is again 2. One, two, three. So this is 3. Then note one more thing, that in any graph we always have a path from a vertex to itself, namely the trivial path consisting of only that vertex whose length is 0. So because of that, the distance of a vertex from itself is 0. Okay, so we keep that in mind also. Since here we are trying to look at all possible distances, so ideally we should have written distance of 1 between 1 and 1, but actually since we are trying to find the maximum possible distance, so there is no point writing those things. Okay, so the distance between 3 and 4 is 1. The distance between 3 and 5 is also 1. And these two distances are both equal to 2. The distance between 4 and 5 is 2. One, two, three. Then the distance between 5 and 6 is 1, and that is also equal to the distance between 5 and 7. And lastly, the distance between 6 and 7 is equal to 2. Here we have the distance between any point and any other point not equal to that point. So we see that among all these values 1, 2, 3, etc., 3 is the largest. It does not, no distance exceeds 3. We have vertices which are at distance 3 from each other, but no two vertices are at distance more than 3 from each other. So that's why diameter of G is 3. So that's what diameter is, maximum possible distance in a graph between two vertices. Okay, now here we then have a proposition. Next, And if we have a graph like this I, then of course diameter is not finite, because we have vertices at infinite distance from each other. So next proposition, one, 3, 2. Every graph G containing a cycle satisfies this inequality. The girth of G is always less than or equal to 2 times the diameter of G plus 1, where the girth by definition is the length of the smallest possible cycle in G, and it's given that our graph has at least one cycle. It's not an acyclic graph, which is a graph having no cycle. So since we want to bound the girth like this, so we will assume a cycle of smallest length. So let C be a cycle of smallest length, or let C be a shortest cycle. That way also we can write. Let C be a shortest cycle in G. We want to, so that means the length of C will be equal to the girth of G. We want to prove that it's less than or equal to this, but to the contrary, let us suppose that it's strictly greater than this integer. Suppose that the girth is strictly greater than 2 times diameter of G plus 1. Then, since these are all integers, so this inequality is equivalent to this one, 2 times diameter of G plus 2. Hence, there exist two vertices in C such that the distance between them in C is at least diameter of G plus 1. Why though? Why suddenly and exactly how are we able to conclude this thing? Let us see. So we have a cycle like this. We don't really know the exact length. I mean, we know the length of the cycle, but that is also arbitrary. So the cycle C of shortest length or smallest possible length is something like this. One, two, three, etc. It will end at this vertex because its length is g, and we already know, according to the definition of length of a cycle, the length of a cycle, of course, it's the number of edges available in the cycle, but that is also equal to the number of vertices in the cycle. So in this scheme of labeling the vertices of the cycle, we start with one vertex, we call it 1, and then we label like this 1, 2, 3, etc. Now the thing is this: because of this inequality, that g of g is greater than or equal to 2 times diameter of g plus 2, we will have a point that will get the label diameter of g plus 2. Why? Because you see, for such a point to exist, diameter of g plus 2 should be less than or equal to g of g, which is clearly true, because in fact 2 times diameter of g plus 2 is less than or equal to g of g. So this in particular will also be true. So we will get a point like this, and the previous point will get this level, and then it will go with this arbitrary points in between. I mean, we could have just simply put 3 dots here itself. So such a vertex exists. Okay, now we are not going to write anything about this figure. In fact, the figure is not there in the proof given in the text. We are just drawing this figure for our own understanding. Now, we are claiming here that there exist 2 vertices in C here somewhere, such that the distance between them in C is at least this much. Now, what is the distance between 1 and this vertex and this vertex? Clearly, the shortest, okay, and keep in mind that we are saying that this distance we are calculating is in C. That means C is the graph in which we are calculating the distance. Now in C, between these 2 vertices, there are exactly 2 paths. One of them is this and the other one is this. Okay. The length of this path is what? Diameter of G plus 2 minus 1, which is diameter of G plus 1. Why? Because you just calculate the number of edges available in this path, which will be 1 less than the number of vertices. The number of vertices is diameter of G plus 2, so the length of this path is diameter of G plus 1. Now what is the length of the other path? I have not thought about that before. Now only I am thinking. Okay, so let us see what the length of the other path will be. The length of the other path will be the length of the path joining diameter of G plus 2 and G of G plus 1. So that will be GG minus plus 1, and this will be equal to G minus diameter of G plus minus 2 plus 1 will be minus 1, or in other words we will have this. So the other path has length this. Now what happens if this length is actually less than or equal to this length? Okay, but see, so we have got two lengths, two paths, and these two lengths. Now we can make use of this thing, this inequality that we have got from our supposition. This inequality says that the length of this path is actually greater than or equal to this length, because this inequality is equivalent to this one. So that means the path joining 1 and this from this side, that is the shorter one among these two paths. So the distance between this point and this point is actually equal to diameter of G plus 1 in the graph C, that is in C itself. So that's how you get 2 points in C such that the distance between them in C is actually exactly equal to diameter of G plus 1. But you can imagine that if you, instead of calculating the distance between 1 and this point, you can take some other point also lying between diameter of G plus 2 and G of G, then the distance will be slightly greater. The point is that we do get 2 points such that the distance between them in C is at least diameter of G plus 1. Okay. Now what? Now in C their distance is diameter of G plus 1, but according to the definition of diameter, these two vertices in the original graph obviously cannot have this distance, because by definition of the diameter, that is the largest possible distance in G, and this is larger than the diameter. So we write these two vertices are at a lesser distance from each other in G. In the original graph, their distance is smaller than this, of course. So that means there is a path joining these two vertices that is not a part of C, because the length of that path will be smaller than this which is the actual distance between 1 and diameter of G plus 2 in the original graph, and this path has length diameter of G plus 1, or at least this number. So there exists a path P joining these two vertices or in fact there is a path P in G joining these two vertices that is not a subgraph of C. That means even if parts of P are in C, but at some point some vertices in P will go outside of C. For example, say the path between 1 and diameter of G plus 2, that is of length smaller than this that we are talking about, that P, it starts from 1 and then it takes these two values there. I mean these two vertices 1 and 2 and 3, it starts like this, but at some stage here it goes outside. It has to go outside because otherwise it cannot have a length smaller than this. It deviates from C, goes outside, and then it again meets C at some point, either before it gets to this point or it meets this point from outside directly itself. Okay, in any case we will get two vertices X and Y on C at which this deviation occurs, at which the path goes outside of C. There must be two such vertices X and Y in C at which the path joining 1 and diameter of G plus 2 goes outside C and becomes a path of length smaller than diameter of G plus 1, so that the distance between 1 and this is, it gets smaller in the original graph G. So that's why we can write, hence there exist two vertices X and Y in the vertex set of C such that, instead of calling this path P, we can call it P, but let's just give it another name, because P has been used in the text to mean something else, Q. So this is our path Q such that there is a C path XPY in G. Recall that according to the definition of a C path is a path which has, a C path is a path the only vertices of which common to C are these two vertices where it meets the graph C, which in this case is a cycle. That is, it's a path all of whose inner vertices, yes, I was searching for that terminology, all the inner vertices, here we see it looks like a path of length 3, but that's not the thing. There are possibly other vertices in between. So this is the path P. Okay, this much. It starts from here, starts from X, then goes like this and comes and meets C at Y. So the ends of this path are the only two vertices where which are also vertices of C. The inner vertices, these vertices of the path P are not parts of C. So there is a C path xpy in G. This C path along with the shorter of the two paths in C joining x and y gives us a cycle in G of length smaller than G of G. If we consider this path, and now in the cycle there are two paths joining these two vertices x and y. One of them goes like this and comes to y like this. The other one goes like this, and both of the paths are parts of the cycle C. One of them will be the shorter path. If you take the, say if this is the shorter path, this one that goes like that, if this is the shorter path between x and y, then you take this path along with P, you get a cycle whose length is smaller than the girth of G, that is smaller than the length of C. Or if it happens that x and y originally are actually far apart, so that the path joining them in C, that is of the smaller length among the two paths, it happens to lie on this side, then this is the path joining x and y, that is the smaller one. Then you take this path along with P, you still get a cycle whose length is smaller than the girth of G, and this is a contradiction because the girth of G according to its definition is the length of a smallest possible path in G. So this is a do you see why this length becomes smaller than the girth? It's because the girth is the length of C, and since here we are getting a, what should I say, a path, a way in going from x to y in fewer steps than is possible if you go from x to y all the time being in C. That's why using this path instead of this one or this one, as the case may be, we get a smaller cycle than C, and that is the contradiction. So our original or initial supposition is wrong. That is, we must have girth of G less than 2 times diameter, or less than or equal to, I think that's what is given here, less than or equal to, yes, 2 times diameter of G plus 1. So that completes the proof. Okay, now next, another notion. A vertex is called central in G. That means G is a graph and a vertex in G is called central in G if its greatest distance from any other vertex in G, of course, is the least possible this distance is called the radius of the graph G and is denoted by rad G. That is, radius of G is the minimum among the maximum distances. This may seem somewhat actually admittedly quite confusing at first, but we will try to illustrate this with an example and then we will see what the notion is. So what does it mean actually? Let's draw a graph and see what it means. So this is a graph G and these are its vertices 1, 2, 3, 4, 5, 6. Now a vertex will be called central if it has many distances from the other vertices. If the maximum distance, there will be a maximum distance that is the smallest possible. So to understand that, let us calculate all the distances from each vertex. Okay, so when our vertex is the 1, then since there is only one graph, there is no need to write G as a subscript in writing the distances. The distance between 1 and 2 is of course 1. The distance between 1 and 3 is also 1. The distance between 1 and 4 is 2. 1 and 5. Okay, let's just write like this. 1, 2, 3. 1 and 6 is also 3. And the maximum among these distances, that is maximum of 1 and y is 3. For the second one also it will be, you can understand 1 and 2, as far as distances are concerned, there is a sort of symmetry in this graph that makes 1 and 2 alike. That is, 2 will also have similar distances like 1. Distance between 2 and 4 is 2, that between 2 and 5 is 3, and that between 2 and 6 is also 3. So the maximum in this case also the maximum is 3. Then what about 3? D3, 1 is 1. D3, 2 is also 1. D3, 4 is also 1. 3, 5 is 2 and 3, 6 is 2. So in this case the maximum distance is 2. Then 4. 4 and 1 is 2. The distance between 4 and 2 is also 2. The distance between 4 and 3 is 1. Between 4 and 5 is 1. And also the distance between 4 and 6 is 1. So in this case, also the maximum is 2. 2 more vertices are left. Which are also alike. Let me put some ink. I need ink. Five and 1, 1, 2, 3. 5 and 2, that is also equal to 3. Distance between 5 and 3, however, is 2. 5 and 4 is 1, and the distance between 5 and 6 is 2. So the in this case again the maximum is 3, and for 6 you can understand it will have the same result. Distance between 6 and 4 is what? I think I made a mistake. This is okay. We will have 3 here. Yes. Distance between 6 and 4 is 1. 6 and 5 is 2. Six and y. Although all these things look tedious, but just for the sake of understanding, for once we are looking at all the things in detail. So now we look at the maxima, the maximum distances. This one, this one, this one, this one, this one, and this one. Among these maximum distances, 2 maxima are actually the minimum, that is this and this. So that is why 3 and 4 are central vertices. That is, their distances, what should I say, the maximum distance of 3 from any other vertex is 2, which is the smallest possible among all maxima. The same is the case for 4. However, for 5, 6, 1 and 2, that is not the case. So these are central vertices. And this value 2 is the radius of the graph. So that means radius of G, which is the minimum of all the maxima. When we are calculating this thing, this maxima we understood, when among the maxima we are choosing the minimum, then the vertices that give us those minimum values are actually the central vertices. So that choice is made here outside. So that is equal to 2 in this particular case. So this graph has radius 2 and its diameter is 1, 2, 3, which you can easily see why it is 3. These terminologies, diameter, center, radius, these things remind us of circle from ordinary Euclidean geometry. And in fact, the relationship between the radius and diameter of a circle, which is that the diameter is twice the radius, a similar relationship is true here. However, we don't have equality, we have inequality, and that thing is this. Let us now show that for a graph G, radius of G is less than or equal to diameter of G, but diameter of G is again less than or equal to 2 times radius of G. we now next intend to show this, which however we will not do in this video. We will do it in the next video, and in the next video we will see some other things also that are there in this section. Once this section is over, we will go to the next section, which treats connectivity, the concept of connectivity in a graph, which for example identifies some vertices and some edges, removal of which makes the graph disconnected, in the sense that, for example, this graph you would call connected, a graph whose diameter is finite, that is where from each vertex you can reach any other vertex by some path. No matter how long the path is, there will be some path. However, in a disconnected graph, for example, if you remove this edge, then this graph becomes disconnected. In this graph you can never reach, for example, from 2 to 5, there is no path. And the vertices whose removal make a graph disconnected, or more generally make the number of connected components go up, such vertices are called cut vertices, and the correspondingly such edges are called cut edges. So here 3, 4 is a cut edge. Just like that, if instead of removing this edge, if we remove the vertex 3, then of course the edges incident with 3 will also get removed. We will then be left with this graph. So that also gives us, it increases the number of connected components. So that is the cut vertex. So such things will be treated in the next section, and in the next video we will try to finish this section, which has only a few more things. So with this I end this video today. If you have any doubts regarding these things, I keep on saying this, I will continue to say it. You are encouraged to write in the comment section below. And if you are new here, please consider subscribing, it helps a lot. So with this I sign off for tonight. See you in the next part. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.